First I have to open the file, then I have to do it, or what is it?
Sir, so present now I'll click bought to screen share ಮಾಡಿ sir.
ಅದೇ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. 3 ಬರ್ತಾ ಇದೆ. Your entire screen, a window, a tab ಅಂತ.
Screen sir, entire screen.
Entire screen. Okay.
Window.
No, it's not taking.
Sir, ಇದು ನಿಮ್ದು PPT ಓಪನ್ ಮಾಡಿ ಸರ್ ಫಸ್ಟ್.
ಮಾಡಿದ್ದೇನೆ.
ಮಿನಿಮೈಸ್ ಮಾಡಿಬಿಡಿ, ಡೈರೆಕ್ಟ್ ಆಗಿ ಇವಾಗ ಶೇರ್ ಸ್ಕ್ರೀನ್ ಹೋಗಿ ಸರ್. ಇದು
ಒಂದು ನಿಮಿಷ ಇದೆ.
ಎಸ್ ಸರ್,
ಮಿನಿಮೈಸ್ ಆಗಿದೆ PPT.
ಅಲ್ಲ, ಮಿನಿಮೈಸ್ ಮಾಡಬೇಡಿ ಸರ್, ಮಿನಿಮೈಸ್ ಬೇಡ.
ಮಿನಿಮೈಸ್ ಮಾಡಬಾರ್ದಾ? ಓಕೆ,
ಮಾಡಬಾರ್ದು ಸರ್, ಮಿನಿಮೈಸ್ ಬೇಡ, ಹಂಗೆ ಓಪನ್ ಇರಲಿ.
ಹಾ,
ಇವಾಗ ಪ್ರೆಸೆಂಟ್ ನಾವು ಹೋಗಿ ಸರ್, ಅಲ್ಲಿ
ರೈಟ್,
ಅಲ್ಲಿ ವಿಂಡೋ ಓಪನ್ ಮಾಡಿ ಸರ್.
ಓಕೆ, ಯಾ, ನೌ ಇಟ್ಸ್ ಕಮಿಂಗ್.
ಎಸ್ ಸರ್, ಇವಾಗ ಅಲ್ಲಿ ಶೇರ್ ಮಾಡಿ ಸರ್, ಅದನ್ನ ಸೆಲೆಕ್ಟ್.
ಓಕೆ,
ಎಸ್ ಸರ್, ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ರೈಟ್. Good afternoon, everyone. First of all, let me thank SAPTHAGIRI College of Engineering, especially the Department of Mechanical Engineering and Department of Mathematics, who have given me an invitation to present this particular as a resource person to take part in this particular lecture, which is nothing but on general aspects of computational fluid dynamics. So special thanks to the maths HOD, mechanical HOD, who is my close friend, and also Professor Tulsi Das, who was also my colleague earlier in Jain University. I think with these people's love and affection, I just wanted to present this today. I will have to tell you one thing before I start my presentation. Computational fluid dynamics is a very vast thing, but I'm not going to talk anything great about computational fluid dynamics. What I will be talking about is all about the basics, fundamentals. I think I'd start with the importance of fluid mechanics, fluid dynamics. Then I will come to computational fluid dynamics. I think as fast as possible, I will try to cover most of the things. I request everyone, either if you have any questions, either you can make a note of it. We will discuss in the end, or you can stop me at any moment of time. I hope all of you are able to see the screen, right?
Yes, sir. Thank you, and welcome, sir, Dr. Ramanarasimha.
Thank you, sir. Thank you.
Okay, sir. Right.
Right. So these are the contents of my presentation. I'll start with introduction to fluid mechanics. Then I will give an introduction to CFD. We will consider the merits, limitations, and applications of CFD. Then we will try to review some of the fluid flow and heat transfer equations. Then we will talk about partial differential equations, and we will try to consider at the end of the presentation, we will try to consider some practical applications of CFD. So we know that the matter exists in different states as solids, liquids, and gases, but we call liquids and gases as fluids, and solids is a different category. That means that the matter can be mainly classified into two types. One is solids, the other one is fluids. Whenever we ask any question, especially since many students are there in this particular presentation, whenever we ask them the question in the class, what is the difference between a solid, liquid, and a gas and all that, usually the common answer which is given by most of the students is solid is very closely packed, whereas liquid is not that closely packed, whereas the gases are randomly packed, and you know that the liquid is able to take the shape of the container. This kind of things usually we get the answer. But usually we need to understand what is the real difference between a solid and a fluid. The real difference between a solid and a fluid lies in the application of a shear force. If you apply a shear force on a solid, the solid undergoes deformation up to the elastic limit. I repeat that, whenever you apply a shear force on a solid, when the solid undergoes deformation up to elastic limit. Once you remove the shear force, the solid will come back to its initial position. Instead, if you apply a shear force on a fluid, either on a liquid or on a gas, if you apply a shear force, the fluid tends to move. This property of tending to move, we call it as fluidity. That is why such a state of matter, we call it as fluids. I repeat that, whenever you apply a shear force on a fluid, it tends to move. since it tends to move, such a kind of matter we call it as fluid, because that property we call it as fluidity. That is why such a kind of matter we call it as fluids. So, whenever you remove the shear force from the fluid, it will not come back to its initial position. Instead, it comes to rest. This is the actual difference between a solid and a fluid. You know that the matter of our interest is fluids. Fluids are mainly classified into two types. One is liquids, the other one is gases. We all know the difference between liquids and gases. Liquids are known as incompressible fluids. Gases are known as compressible fluids. So, in case of liquids, the density of the fluid remains constant during the flow, whereas gases, in case of gases, the density of the fluid changes from point to point during the flow. Then we have a special kind of fluids, category of fluids known as Newtonian fluids and non-Newtonian fluids. Usually there is a law known as Newton's law of viscosity. So if any fluid obeys Newton's law of viscosity, such a fluid we call it as Newtonian fluid. If any fluid does not obey Newton's law of viscosity, such a fluid we call it as non-Newtonian fluid. I'll come to Newton's law of viscosity and I'll come to the examples for Newtonian and non-Newtonian fluids later. Now the question is, why we are giving lot of importance to fluid mechanics, not only in this particular workshop or FTP, even other than that also. Usually fluid mechanics is one of the thrust area. Why we consider fluid mechanics is most important, that is what is the thing. So first thing is, fluid is very much essential to life. It is found that almost 65% of the human body contains water. Earth's surface is surrounded with 2/3 of water. So atmosphere extends 17 kilometers above the Earth's surface, and even there is a historical background for the importance of fluid mechanics. Not only this, you know that the fluid mechanics equations we have frequently taught to the students. Students have heard of it, and we have frequently referred to these things: Archimedes' principle, Newton's second law of motion, Bernoulli's equation, Euler's equation, Navier-Stokes equation, Reynolds number. So many things we have taught in the class. But I don't know whether we are really shown the scientists who are really responsible for this kind of concepts. So I would like to I would like to present this particular slide where you can see the photographs of all these scientists. If these scientists would not have been there today, fluid mechanics concepts would not have been there. So that is why I think it's very important to give the respect to these scientists, but at least by seeing their photographs, we'll try to respect them. So you can see the photographs of Archimedes, Newton, Bernoulli, Euler, Navier, Stokes, Reynolds, and all such people here. Now I will not go to this. We all know this. Fluid mechanics is a branch of science which deals with the fluids either at rest or in motion. So fluid mechanics can be mainly classified into three types: fluid statics, fluid kinematics, and fluid dynamics. The study of fluids at rest we call it as fluid statics. The study of fluids in motion without considering the external forces acting on the fluid, such a branch we call it as fluid kinematics. The study of fluids in motion considering the external forces acting on the fluid, such a branch we call it as fluid dynamics. Now anyway, the importance of today's topic is related to fluid dynamics only. If you ask me what are the applications of fluid mechanics, I will ask you in turn where exactly applications of fluid mechanics are not there, right? Because there are plenty of applications of fluid mechanics, starting from aircraft, surface ship, right, and air pollution, river hydraulics, blood pump, water sports, hurricanes, and so many things. If you consider the machine wise, that is, which are the machines which operate based on the concept of fluid mechanics, there are many machines. Many of them, that is, the prominent of them include engines, turbines, compressors, pumps, rockets, jets, heat exchangers, etc., etc. Okay, there are two approaches which we usually commonly use in fluid mechanics. One is known as Lagrangian approach. The other one is the Eulerian approach. In the Lagrangian approach, each and every fluid particle is followed during its motion. So you know that during the motion of a fluid, there are many fluid particles which are flowing. But each and every fluid particle is followed during its motion. And for each of the fluid particle, we try to measure the velocity, pressure, density, etc. Whereas in the Eulerian approach, we don't follow each and every fluid particle. Instead, we allow the fluid particle to pass through a cross section. At that cross section, we try to measure the velocity, pressure, density, etc., etc., and the other properties of the fluid particle. So the second approach is little easier compared to the first approach, because in the first approach, you are supposed to follow each and every fluid particle. It is very, very difficult. And you are supposed to describe the properties of each and every fluid particle in the first approach. So that is the reason why in fluid mechanics applications, usually Eulerian approach is commonly used compared to Lagrangian approach. Now let me come to this. So we have different types of fluid flow like steady, unsteady, uniform and non-uniform, laminar and turbulent, compressible and incompressible, rotational and irrotational, one-to-one, three-dimensional. I will not go to the details of this. In some of the cases, the fluid properties vary with respect to time, do not vary with respect to time. In some of the, that is in uniform flow, non-uniform flow, velocity is not a function of space. In non-uniform flow, it is a function of space. Like this, compressible and incompressible, we are considered already. Like this, we have different types of fluid flow also. Now, I think I would like to concentrate more on this, because all this particular FTP, especially whatever we are talking about, computational fluid dynamics or fluid dynamics, everything is based on the fundamental equations of fluid mechanics. So what are the basic equations of fluid mechanics? These are the basic equations which can be listed. Without this, none of the fluid dynamics concept, none of the fluid kinematics concept, none of the fluid statics concept can exist. So what are those equations? It starts with Newton's law of viscosity, then Pascal's law, then hydrostatic law, then we have the continuity equation, then we have the equation of state, then we have the momentum equation. Finally, we have one more last equation known as energy equation, which can also be called as Bernoulli's equation. So what are they? One by one, let us try to consider. Newton's law of viscosity, I have already told you. Based on Newton's law of viscosity, we classify the fluids as Newtonian fluid and non-Newtonian fluid. So what is that Newton's law of viscosity? Newton's law of viscosity states that the shear stress exerted between two fluid layers is directly proportional to rate of shear strain. Any fluid which obeys Newton's law of viscosity, we call it as Newtonian. Any fluid which do not obey Newton's law of viscosity, we call it as non-Newtonian. You know that there are plenty of examples can be given for Newtonian, including water, air, petrol, kerosene, diesel, etc., etc. They are all Newtonian fluids. But if you ask the student or even the teachers also to list some of the non-Newtonian fluids, I don't know how many of them are able to list it. Let me tell you now, there are plenty of non-Newtonian fluids. Our blood is a non-Newtonian fluid. Toothpaste gel is a non-Newtonian fluid. Butter is a non-Newtonian fluid. All plastic fluids are non-Newtonian fluids. Suspensions, slurries, they are all nothing but the non-Newtonian fluids. So then let us come to Pascal's law, which we are going to study in hydrostatics, that is in fluid statics. According to Pascal's law, the pressure at a point in a static fluid is same in all directions. That is, if you consider the pressure in x direction, y direction, and z direction in a static fluid, that remains the same in all directions, whether you consider it in x direction, y direction, or in z direction. Then let me come to this hydrostatic law. According to hydrostatic law, basically hydrostatic law says that the pressure head of a fluid is the ratio of pressure of the fluid to its specific weight. P is the pressure of the fluid, rho g is the specific weight. The most important application of hydrostatic law can be observed in a swimming pool. You know that we usually say that swimming pool has got a depth of 4 feet, 5 feet, 6 feet, like that. And usually it is a common tendency to ask the question, if you go to a depth of 2 feet inside water in a swimming pool, what will be the pressure? And if you go to a depth of 4 feet inside water in a swimming pool, what will be the pressure? You know, all of us know that if you go to a depth of 4 meters or 4 feet, then the pressure will be more there rather than at 2 feet. That means as the height increases, the pressure also increases. That is very much evident. That is proved by hydrostatic law only. That is how the hydrostatic law takes a very, very important role in such of the applications. Now let us try to define two very important non-dimensional numbers, especially these two numbers take lot of significance in the study of computational fluid dynamics. One is the Reynolds number, the other one is the Mach number. Usually Reynolds number is the non-dimensional number used to predict the nature of incompressible fluid flow. Mach number is a non-dimensional number used to predict the nature of compressible fluid flow. Whenever we are analyzing a liquid, we analyze it through Reynolds number. Whenever we are analyzing the flow of a gas, we analyze it through Mach number. So Reynolds number is defined as the ratio of inertia force to viscous force, and it is a very important non-dimensional number in compressible fluid flow, which signifies the nature of flow. It says whether the flow is laminar or turbulent. Similarly, a Mach number is defined as a square root of ratio of inertia force to elastic force, and that is a very important non-dimensional number used in the compressible fluid flow, and it signifies the nature of flow in a compressible flow. Based on the value of Mach number, we can say whether the compressible flow is sonic flow or subsonic flow or supersonic flow. Now let me come to fluid dynamics. You know, fluid dynamics is a very important branch of fluid mechanics which deals with the fluids in motion, considering all the external forces acting on the fluid. So what could be, whenever the fluid is in motion, what could be the different forces which could act on a fluid? There are different forces which could act on a fluid, like force due to pressure, force due to viscosity, force due to turbulence. Sometimes there are some body forces. What do you mean by body forces? Body forces are the forces due to self-weight of the fluid. Then there could be some forces due to surface tension, etc. So now let me, before I start with the concepts of CFD, let me come to CFD now. Usually why CFD is very important, because you know, to analyze the fluid flow, you can do that using three important methods. One is the experimental method. The second one is known as the theoretical method. Third one is known as the numerical method. Whenever I consider a fluid flow problem, I can also solve such a problem even for heat transfer also. So that is why whenever I talk about fluid flow problem, I join even heat transfer also with that, because to solve any heat transfer problem or to solve any fluid flow problem, three approaches can be used. One is the experimental approach, second one is the theoretical approach, third one is the numerical approach. That numerical approach, we call it as CFD. Let me come to that later. First we talk about experimental approach, theoretical approach, even numerical approach also. Then we try to compare all the three. Then we, in particular, we talk about the numerical approach. So what is the comparison of the three methods? This is the comparison of three methods. First, we will try to consider the experimental method. The table shows both the advantages as well as the disadvantages of experimental method, analytical method, as well as the numerical method. You know that the people who are doing PhD, who have already completed PhD, especially the faculty members, you might have heard already that your PhD will have more value if you have anything substantiated with experimental results. If you don't have the substantiation with experimental results, then validation may be a big problem. So you may validate it with some literature or something, that is a different case. But experimental results are more courageous and they are going to be respected more compared to analytical results or numerical results. Why experimental results are respected more? It is because experimental results are capable of more realistic. We have an equipment with us and we have the ready-made, or we have got the proven values with us, right? With all this, we can prove a concept. So that is why the experimental methods or experimental results are more respected compared to analytical results or numerical results. There are disadvantages also in the experimental approach. You know, to do any experiment, equipment is required. So the equipment will be very, very costly. There may be a scaling problem. For example, if you want to do the experiment with a hydraulic turbine, you cannot build the experimental setup of the actual hydraulic turbine. You will have to build a small one. So how do you scale it is the problem. Then there are measurement difficulties. You will have to measure the velocity, you will have to measure the temperature, you will have to measure the pressure. For those things, a lot of sensors are required, which are very costly. Then the operating cost of the experimental method is very, very high. Then what is the other approach? We have another two approaches. First one is analytical. So analytical approach means what? You have some equations, ready-made equations, substitute the values in the equation, get the result. But the problem with the analytical approach is, in most of the analytical approaches, most of the equations are linear equations. Since most of the equations are linear equations, they may not be able to solve a real-time problem where the equations may not be linear. So first let us consider the advantages of analytical method. Analytical method is a clean method. It will give you general information, and the information will be in the form of an equation or a formula. What are the disadvantages? As I told you already, the analytical methods are restricted to simple geometry and physics, and they are usually restricted to linear problems. They will not be able to solve a non-linear problem. So that is why the third method comes into picture. So the third method, overall we call it a CFD. Let me come to that later. But basically it is known as the numerical method. So the advantage of numerical method is no restriction of linearity. It is capable of solving some non-linear problems also. And it is complicated physics can be treated properly in a numerical method. But the disadvantages are also there in the numerical method. Truncation errors are more in the numerical method. Boundary condition of the problems are to be defined properly in a numerical method. If you don't define your boundary conditions properly, for whatever wrong boundary condition you have defined, for that you get some nonsense result. That nonsense result may not be able to, you may not be able to match that with the reality. Then computer cost, you might have heard of people, sometimes whenever you run a CFD program, it will run for 1 week, 4 days, 5 days to get one result. So computer cost, its speed, all those things will matter in numerical result, in numerical approach. So that means any heat transfer problem, any fluid flow problem can be solved using three methods: experimental method, analytical method, numerical method. All the three have got their own advantages and disadvantages also. But our focus of interest for today is the numerical approach, which we call it as computational fluid dynamics. So then, what is computational fluid dynamics? Computational fluid dynamics, as it is said, it is computational fluid. That means we are trying to solve a fluid dynamics problem using a computational method. Such a thing we call it as computational fluid dynamics. So CFD is going to predict what will happen or what may happen quantitatively when the fluid flows with these conditions. What are those conditions? There could be a simultaneous flow of heat apart from fluid flow. There could be simultaneous flow of heat apart from fluid flow. There could be simultaneous mass transfer apart from fluid flow. There could be simultaneous phase change apart from fluid flow. There could be some chemical reaction apart from fluid flow. Sometimes there may be mechanical movement also. CFD can handle this kind of problems. So then, what are the steps involved in CFD? First, we need to understand the physics of the problem. What do you mean by physics of the problem? Let me give you an example. Let us say that I will take a very simple example. Water is flowing through a pipe, right? When the water is flowing through a pipe, you know that what we need to measure there or what we need to predict there, maybe one is the velocity of the fluid. The other one is what may be the pressure at the inlet, what may be the pressure at the outlet. To do this, first we need to understand the physics of the problem properly. Then we'll have to do the modeling. Then we'll have to define the proper boundary conditions. Then we'll have to solve it numerically. Then we should present the results in the form of visualization. So all these things, if you, the same example, if you want to complicate it a little bit more, I will say that water is flowing through a pipe, but the pipe is kept in the sunlight at 12 o'clock in the afternoon. It is kept in the sunlight. What happens now? Sunlight is going to be there on the pipe. Naturally, the pipe surface gets heated. From the surface of the pipe, the heat is transferred to water. So there may be conduction effects, there may be convection effects, there may be radiation effects also from the sunlight to the surface of the pipe. All these things can be added apart from solving the pressure of the fluid and the velocity of the fluid. All these things are going to be dealt in a proper way in computational fluid dynamics or CFD. So what is that we do in CFD? The objective of CFD is to model the continuous fluid with a partial differential equation, and we try to discretize partial differential equation into an algebraic problem. What do you mean by that? So you know that if the fluid is flowing through a pipe, the length of the pipe is 2 meters. You divide that 2 meters into many number of parts and try to analyze it segment wise. So that we call it as discretization. Then try to convert the physics of the problem to either to an ordinary differential equation or to a partial differential equation. Then try to solve that ordinary differential equation or partial differential equation using some suitable method. This is what we do overall in CFD. Okay, now the next thing, I have given the heading as where is CFD used. I should give the heading as where CFD not used. In fact, nowadays where CFD has become a trend, it is used everywhere, including in aerospace, automotive, biomedical, chemical, hydraulics, marine, oil and gas, power generation, sports, etc., etc., etc. So the figure, what you can see in this slide, also shows that temperature and natural convection currents that is solved using CFD. Right? Anyway, I will not go to the details of that. So you can see some more things which are solved using CFD technique. The first one is flow around cooling tower. The second one is streamlines for workstation ventilation. So these are some of the things, studies which are carried out using CFD. Now you know that nowadays, even in biomedical science also, people are using CFD. The blood pressure can be controlled using CFD, right? And also the blood pumping to the brain and all that can be analyzed using CFD, right? And urine, what is the urine amount and all that can be predicted using CFD. So a lot of applications are there, even in biomedical sciences also using CFD. Already our doctors are using this technique to predict all this. So now the question is, can CFD be really trusted? If you ask me personally, I say that no, you cannot trust CFD completely. Why you cannot trust CFD completely? I will come to the details of that little later. Now I should say now, importantly, three important things. First thing is the input data may involve too much of guesswork or imprecision. That means what? You know, let us say we wanted to solve an equation using Navier-Stokes equation. Navier-Stokes equation has got a lot of terms. So it is very difficult to solve all those terms together. So that is why what we try to do, we try to do some assumption and then try to solve the equation. When you try to do some assumption, you will get the result, but it may not be exactly nearer to the actual one. So that is the major problem with CFD. The available computer power may be too small for high numerical accuracy. The scientific knowledge base may be inadequate. I think that is the most important thing. The last one, scientific knowledge base may be inadequate in the sense, whatever boundary conditions we give, it may be wrong because of our less knowledge about the physics. If we have defined the physics itself wrongly, naturally the result will also be wrong. That is why CFD cannot be 100%. Reliable in solving single phase flow rather than solving multi-phase flow. CFD solutions can be more reliable for chemically inert gases rather than chemically reactive materials. The CFD results are more reliable for simple fluids rather than those of complex composition. So therefore, for everything you cannot depend on CFD, but you cannot leave CFD also. Why you cannot leave CFD? At least using CFD, you can predict you can get to know what may happen when you test it in a real-time condition. So that is why CFD is of course important, but you cannot depend completely 100%, you cannot depend on CFD. Then whatever I told you, I have just put it in the form of a flow chart here. First, we need to understand the fluid mechanics, whether it is an inviscid flow we are talking, viscous flow, is it laminar, is it turbulent flow, is it compressible flow, incompressible flow, all those things we need to understand. Then we are supposed to convert the physics in the form of equations. After converting the equations, we'll have to solve it using some proper numerical method. Then we will have to analyze the results. This is all about CFD. Okay, I have told you already. So first you will have to do the discretization. Then use to do that. After discretization, convert the physics of the problem to either ordinary differential equation or partial differential equation. Then that will get converted to system of algebraic equation. Try to get the numerical solution of these equations using a proper condition. But to do this, usually in CFD, we use three important methods. One is the finite difference method. The second one is the finite element method. Third one is the finite volume method. Usually finite difference method is based on the differential equations. Finite element method and finite volume method, most of the times they depend in those finite volume method, in finite element method, we try to convert the physics of the problem in the form of integral equation. Rather than converting it in the form of a differential equation, we try to convert it in the form of a integral equation. Okay, what are the flow conditions usually which you will come across while studying CFD? Usually the flow may be viscous or inviscid. Either it could be external flow or internal flow. It could be laminar flow or turbulent flow, either compressible or incompressible flow, single phase flow or multi-phase flow, or it may include the thermal effects, density effects, etc., etc. Okay, now before I conclude, I will take only another 5 minutes. After that, I will allow you people to for any discussion, any questions. But before that, let me talk about some basic equations. Let us start with continuity equation. Now, I don't want to go to the equation. Let me only tell you the overall meaning of continuity equation. Continuity equation is based on law of conservation of mass. According to law of conservation of mass, whatever is the amount of fluid which is entering a section, the same amount of fluid should leave the section. Mass of the fluid entering a section should be equal to mass of the fluid leaving the section. Usually, these equations are written in three-dimensional fashion, two-dimensional fashion as dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w plus dou rho by dou t equal to 0, etc., etc. You know, further, these equations can be reduced for a study in compressible fluid flow as dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0 and all that. Now, the next one, I take only 2 to 3 minutes for this particular slide because the entire fluid dynamics depends on this equation, which we call it as momentum equation, also known as the Navier-Stokes equation. Navier-Stokes equation looks like very simple. It is based on Newton's second law of motion. We all know Newton's second law of motion. According to Newton's second law of motion, we know that F equal to ma. The problem looks like very simple, F equal to ma. But the problem is not so simple. Any questions? Any questions? Okay, let me continue. So the problem is not so simple. Even though we say that F equal to ma, problem is not so simple because the left-hand side, which is nothing but the force, there are different type of forces like force due to pressure, force due to surface tension, force due to gravity, force due to viscosity, etc., etc. And these forces could act in x direction, y direction, and z direction. If you come to the right-hand side is mass into acceleration. So acceleration of the fluid may be there in x direction, y direction, and z direction. Keeping all this in mind, we have written in x direction, y direction, and z direction, we have written the momentum equation. This momentum equation, we also call it as Navier-Stokes equation. I will consider only the x direction equation. What you can see on the left-hand side, what is written as x that is nothing but the body force. What is written as dou P by dou X, that is nothing but force due to pressure. What is written as nu into dou square U by dou X square plus dou square U by dou Y square plus dou square U by dou Z square, that is the force due to viscosity. On the right hand side, the term whatever is indicated is nothing but the acceleration. As you can see here, the momentum equation in X direction, Y direction, Z direction, if you try to solve that simultaneously in all the three directions, it's very, very difficult to solve because there are so many terms involved in this. That is why we try to do some assumption. What kind of assumption? Sometimes we tell that there is no viscosity. Sometimes we tell that there is no force due to pressure. Sometimes we tell that there is no body force. Sometimes we tell that the acceleration of the fluid is zero. By doing this kind of assumption, then only we try to solve the Navier-Stokes equation or the momentum equation. At this juncture, I should tell you here that so far, the solution of Navier-Stokes equation is one of the thrust area. Nobody is able to solve the Navier-Stokes equation keeping all the terminologies of the equation intact. Nobody is still able to solve the Navier-Stokes equation completely. Whatever solutions available for Navier-Stokes equation, all those solutions are with lot of assumptions only. So that is why this equation plays a very important role in the solution of CFD. Then the energy equation, which we also call it a steady flow energy equation or Bernoulli's equation, which we write in the form of P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2 and all that. All these kind of basic equations are used in computational fluid dynamics. And whenever there is a heat transfer which comes into picture, we use the heat conduction equation like dou square T by dou X square plus dou square T by dou Y square plus dou square T by dou Z square plus Qg by K equal to 1 over alpha into dou T by dou T. Of course, anyway, this is only in Cartesian coordinate. Similar kind of equations to be considered even in cylindrical and spherical coordinates also it can be considered. Now, the most important thing is, I have told you already, in any CFD problem, first you will have to understand the physics, convert the physics to a differential equation. Most of the times it could be either ordinary differential equation or it could be a partial differential equation. So the partial differential equation play a very important role in the CFD solution of a problem. The partial differential equations can be classified into two types as mathematical classification and physical classification. So mathematical classification based on order, you can classify partial differential equation as first order, second order PDE, third order PDE. Based on linearity, you can classify them as linear partial differential equation, quasi-linear partial differential equation, and non-linear partial differential equation. Then based on whether b square minus 4ac is less than 0, equal to 0, greater than 0, based on that you can classify that as elliptic equation, parabolic equation, or hyperbolic equation. So based on physical classification, it can be classified into two problems. One is known as the equilibrium problem, the other one is the marching problem. In the equilibrium problem, you can get the solution then and there only. In a marching problem, always results in a set of simultaneous equation. Until and unless you solve those simultaneous equation, you will not be able to get the solution in a marching problem. Okay, now I don't want to tell you more theory. Before I end my talk, let me show some of the important results what we have obtained through CFD. It's not done by me. In fact, I have taken it from different sources. So you can see the animation of liquid filling in a tank, three-dimensional flow. Then you can see the vortex shedding behind a cylinder. This is a two-dimensional flow. This is again a three-dimensional flow, vortex shedding in a cylinder. This is the flow in a turbocharger. And this is the flow in a centrifugal pump. This is the flow through passage between stator and rotor blades, maybe in a turbine or in a compressor, especially in turbo machines and all that. And finally, CFD did not leave the toilet also. It has come to toilet flush also. So you can see how exactly toilet flush can be analyzed using CFD. So let me summarize now. In this session, we have discussed about the basics of fluid mechanics, the basics of CFD. merits and limitations of CFD. We have also considered the procedure involved in CFD. We have reviewed the basic equations of fluid flow and heat transfer. Then finally, we discussed some of the practical applications of CFD. I think these are the things what we have discussed today. So let me thank once again Sapthagiri College of Engineering, especially Department of Mechanical Engineering and Department of Mathematics for inviting me to share my experience with CFD. Thank you one and all. Let me close my session, but if I have any question, I am very happy to take it.
Hello. Hello.
Hello.
Any questions from participants? Hello. Hello. Any questions? Let me assume that there are no doubts.
Sir,
Hello?
people will not get the doubt only in two cases. If they have understood everything, they will not get the doubt. If
No,
they have
sir.
not understood anything, then also they will not get the doubt.
No, sir. Being a fluid dynamics man, I am also a fluid dynamics person. Your lecture was fantastic, sir. We started from basic. I wish your session would have been the first session of our.
Correct.
What I feel, sir. Thank you, sir. Now I request HOD Mechanical to render vote of thanks, sir.
Thank you, sir. Ramanarasimha sir, mathematics HOD ಏನ್ ಹೇಳಿದ್ರು ಅದನ್ನೇ ನಾನು ಹೇಳ್ಬೇಕು ಅನ್ಕೊಂಡಿದ್ದೆ. Your session supposed to be the first session because fluid foundation, even for mathematics also, whatever you have given, that is the foundation. Starting from analytical, experimental, so mechanical, numerical, all methods, even for mathematics, start from the concept. So you have given wonderful talk about the basics, total foundation you have given for CFD. It was excellent and also interesting, sir. So really, it was very interesting session. So on behalf of Sapthagiri College of Engineering and Department of Mechanical Engineering and Mathematics Department, so I thank you very much for your wonderful session, sir. And also thank you very much for you accepted readily as soon I and our mathematics HOD asked to participate in this FDP. So once again, thank you very much. And
thank you. It's
I
my
also
pleasure.
thank our management, Principal Dr. H. Ramakrishna sir, the convener of FDP, Dr. Sripant Markandeya sir and team, all the participants, and also few students joined in this session, especially for this session. I thank the students also. So thank you one and all.
Thank you, sir. Thank you so much for the opportunity. It's my pleasure to be there in this session. Thank you.
Now there is a note for participants. The session is the first lecture of second session of day 3 is over. If you have got any questions, or if you want to contact principal sir of KSSEM, definitely you can. He is definitely very much helpful to you. I feel that most of the faculty who want to teach fundamentals of fluid dynamics must take the advice from Ramanarasimha sir. This is what I feel.
100% true, sir.
We close the session now. I think Dharmendra Tripathi professor is also there. Please, we shall join at 3:30, sir. We shall have 15 minutes rest. I think it's okay. Hello. Hello. We shall meet at 3:30 then. ಇಲ್ಲ ಇಲ್ಲಿ ಹೋಗಿ ಸ್ಟಾಪ್ ರೆಕಾರ್ಡ್